Hello, everyone, and welcome to week 4 of Geology 100 lecture. Our topic of this week is the theory of continental drift in plate tectonics. Now, if you are in and enrolled in the Geology 100 lab currently, we've already discussed plate tectonics, and that was in week 2 of your lab. So for this week, we're going to dive deeper into the actual details of plate tectonics. Plate tectonics in itself is a very well-developed theory, and one that really didn't come about until the 1960s. But there's all this working beforehand in these preconceived thoughts and theories that came well before plate tectonics. One of the earliest ideas were that the continents were fixed in place, that the surface of the Earth was in fact immobile. Now that is very much the earliest idea. And that early idea stuck for centuries. You've probably heard of Alfred Wegener, who's one of the most famous geologists behind the theory of continental drift, which was then born and birthed into a more well-developed theory called the theory of plate tectonics. So today we're going to talk a little bit about the beginnings, those ideas that came well before plate tectonics. And then we're also going to divulge a little bit deeper into what plate tectonics is. The theory of continental drift is exactly what it says, the theory that the continents have drifted and are moving through time, but not fast, very, very slowly, as you probably have learned in Geology 100 lab. So where does this bring us before the famous Alfred Wegener? That wasn't until later on in the 20th century. In 1596, the first kind of ideas about this fixed position of the continents was challenged, and that was first challenged by Abraham Ortelius. And Abraham Ortelius had speculated the continents might have moved at some point in geologic time. He couldn't provide any more concrete details behind this idea. Now, his idea was later supported by a handful of scientists, as you can see here on the slide. But it wasn't until about 300 years later when James Dwight Dana came along in 1849 and heavily rejected the work of Ortelius. Now, he claimed that the continents are fixed in their position, that through time, the Earth had slowly cooled, and as it was cooling, that molten rock had formed these continents, and that these continents are just fixed in their position and when this original molten rock had originally cooled. His ideas were later confirmed by the Challenger expedition that was from 1872 to 1876. And he confirmed this idea of looking at the continental shelves. And he said, oh, it looks like the continents have these roots that are extending all the way into our oceanic crust. Therefore, the continents are fixed in their position. If they are fixed in their position, how do you explain our very vast changes in topography? So our really low lows in the oceans and the very highs in our mountains. He explained the formation of the mountains as Earth's interior was slowly cooling. And because it was cooling, it was shrinking. And as it was shrinking, the pressure of the shrinking was pushing on the very edges of the continents. And thus that pressure was then forcing certain areas of that continent to then amass up and bulge up. And thus the mountains had been born. What came about was 70 years later was Alfred Wegener, who you all very much know. He was one of the first scientists that came about in centuries that challenged these long-standing notions that the continents were immobile. And he challenged this in a very drastic way. He published a book entitled The Origin of the Continents and Oceans. And in this, he stated that there was at some point a supercontinent. That supercontinent he named Pangaea. He had stated that approximately 200 to 300 million years ago, that all of our present-day continents that we see in their fixed positions right now were actually pushed together in a supercontinent. And since then, they have drifted. And thus was born the theory of continental drift. Wegener's idea, this theory of continental drift, essentially was the basis of a very large scientific revolution. He was a scientist, and a scientist of scientists that challenged other scientists, and specifically geologists, in this long-standing notion. He believed that Earth has continually changed through time. And the last big supercontinent, where we have seen all these continents fit together like a jigsaw puzzle, was during the supercontinent Pangaea that he theorized was 200 to 300 million years ago. With the theory of continental drift, he believed that the continents would move, they would split apart, and they would recombine. In this splitting apart and recombination of these continents through time, ocean basins were also opening and closing. So new oceans were being birthed. Oceans were being closed and cut off, right? He theorized that in our past, that Earth's surface had looked very much different. So he challenged the ideas of James Dwight Dana, and those that James Dwight Dana had confirmed through an expedition. So here comes along Alfred Wegener, creating this big revolution, and thus was born this theory of continental drift. And we'll get into some of his other observations as well. Alfred Wegener presented many observations that he used to help back this idea of the theory of continental drift. He had 5 main observations. And the first one we've already talked about, which is the continental fit of the continents. They look like jigsaw puzzle pieces where they can just fit together like a jigsaw puzzle. The other 4, which we'll hop into right now. The first one is glacial evidence. So we have the evidence of past glaciation that currently reside on continents that are very close, if not directly on the equator. And we know that glaciers can't exist and persist in very much lower latitudes closer to the equator, where you are in a subtropical to tropical zones. It is just too warm. So he believed that when supercontinent Pangaea was all pushed together at one point, that the supercontinent was pushed at a much higher latitude. So likely in the reaches of the Arctic regions, where you can have the persistence of glaciers on these continents. And then as those continents are then splitting apart and breaking after the formation of the supercontinent Pangaea, those glaciers had then melted off, and now those records have remained on continents. The next line of evidence is paleoclimatic evidence. Now, Alfred Wegener believed that there were these climate belts that had once existed during supercontinent Pangaea. And a lot of these were recorded in sedimentary rocks. And one of them that he noticed, which I'll give an example of, are the presence of coral reefs. And now we have these climatic belts that had once persisted during supercontinent Pangaea that are now scattered across these continents in a range of latitudes today. The next observation that Alfred Wegener had was fossil evidence. And so what he believed that supercontinent Pangaea, where you had these persistence of certain species of organisms, where now these remains are just like the paleoclimatic evidence, are scattered across continents. So how can you have similar species of organisms in the remains scattered across continents if they were persisting at one period of time? Which means that if the continents were in their fixed position, that these organisms would have to swim across oceans in order to mate and breed and reproduce. So this idea that during the supercontinent Pangaea, these organisms can freely move from one continent to another. And when they broke up, the continents, those remains, are now scattered across latitudes on these various continents today. The final observation is the matching geologic units, where there are distinctive rock assemblages that match across the Atlantic. A really good example would be the Appalachian Range, which is in the eastern part of North America and extends up through some remnants in Greenland. That this rock type matches with the Caledonites in the western and central parts of Europe underneath the Scandinavian peninsula. So if these continents were at once a supercontinent, and the eastern portion of North America was in line with the western and central portions of Europe, then these rock units could have formed at one time. Once they split apart, those records would obviously remain, and those are what we see today. Unfortunately, Alfred Wegener's theory was promptly rejected, and the biggest one is that when he went to a conference, presented this work, the biggest backlash that he got was he couldn't explain how these continents have moved through time. And then the explanation is the mechanisms and the forces that could possibly move the continents in the first place. One of his ideas for mechanisms would be the rising and falling of tides. That's simply just not enough in order to move continents literally thousands of kilometers over the course of 300 million years. So because he couldn't explain the mechanisms and forces that could possibly move the continents, what does that leave us with? His 5 main lines of observations are ones that we still accept today in the geologic realm. But it's the mechanisms and forces that he couldn't explain. Before World War II, we knew a ton less about the shape of the ocean floor than we did the surface of our moon. It was very much easy to take a telescope and look at images of the surface of the moon. But it's not as easy in order to study the profiles and the workings of our seafloor. So before World War II, there's an expedition that came about that was 4 years long that pursued to study the bathymetric profiles of our seafloor. With about 360 of these images, they noticed a bunch of different things. They noticed abyssal plains, so long expanses of just flat line ocean floor. They noticed these symmetrical mid-ocean ridges, which we'll come to a little bit later on. They noticed these fracture zones, which are offsets along these mid-oceanic ridges. One of the things that they also really noticed were these deep sea trenches. I also noticed these what looked like mountain ranges on the ocean floor. So what could explain these differences in our ocean floor when we had once thought it was just the continents with the continental shelf and just kind of plateaued out into the next continent, which in fact, there are a bunch more topographic changes in our ocean floor than we had ever realized before. So the only thing that could possibly explain this was Alfred Wegener's theory of continental drift, and thus plate tectonics. In the mid-20th century, geologists knew a ton about sediment accumulation on Earth's surface, with a lot of it, the sediments, moving from terrestrial regions into our oceans through the introductions of rivers and streams. So if we have about 4.5 billion years of Earth history, we would expect to have a ton of sediment accumulation along the continental margins. However, through these bathymetric profiles, they realized that at its thickest, we see sediment packages no thicker than about 1 kilometer. But if we know sediment accumulation rates, and we know the age of the Earth, we realize, and geologists had realized, that the accumulation of sediment should be much thicker than it actually is. So what does that leave us, where we have relatively thin accumulation of sediment along continental margins, and it seems to be thinning as we're moving towards the mid-oceanic ridges. Thus came along Harry Hess and proposed a mechanism to explain these changes in sediment thicknesses. And he realized 2 things: that the thin ocean sediments must mean that the oceanic crust closest to the ridge axis must be younger than the oceanic crust that's right next to the continental margins. And thus, the second line of evidence and observations that he had was that the thinning of these oceanic sediments closer to the mid-oceanic ridges shows that the oceanic crust gets older as you move away from the mid-oceanic ridges. In the late 1950s, Harry Hess, after studying the observations that I previously just talked about with the changes in sediment thickness as you're moving away from the mid-oceanic ridge axis, stated that the ocean floor must be a lot younger based on those sediments than the continents itself. And thus he proposed, which would be later coined and named by Robert Dietz, he proposed a mechanism called seafloor spreading. Now this mechanism instantly provided backing for Alfred Wegener's theory of continental drift. Now with seafloor spreading, he proposed that at these mid-oceanic ridges, you have this upwelling of this very hot mantle. And as it pushes its way through these cracks and fissures at these mid-oceanic ridges, it breaches in the form of lava, and that lava instantly cools. Now, this breaching of this hot magma, this mid-oceanic ridge axis, is enough force in order to push this oceanic crust towards the continent. Now, this oceanic crust, because it is much younger and thus much thinner, as he believed, than the continental crust, must then get swallowed underneath the continental crust, thus being subducted. So as the continents move apart, because seafloor spreading occurs, you also get the continents moving together as the seafloor is being subducted. As you move through the remainder of the PowerPoint, you are going to come across the terms that are related to seafloor spreading, which is slab push, slab pull, and slab drag. Now, those all relate to how the oceanic lithosphere is behaving with respect to the continental lithosphere. You'll also briefly go into magnetic anomalies, how Earth's magnetic field is created, and how that has affected and thus backed further ideas about plate tectonics and this mechanism of seafloor spreading. For the remainder of this brief video that I have, I do want to talk briefly about plate tectonics, the plates that we have in our modern day, but also the boundaries between these plates and thus how these plates are interacting with one another. Currently, Earth's surface is fragmented into approximately 20 tectonic plates. Now, it says approximately 20 because we do have a tectonic plate that will probably likely be not around for much longer. And that is the Juan de Fuca plate, which is right here on the screen. It is essentially being pushed with the Pacific plate and will underneath the North American plate. So this plate will eventually become recycled and swallowed underneath the North American plate. Through time, geologists have recognized that plates move continuously at a rate of 1 to 18 centimeters per year. Now, on the average, that's about 3 to 5 centimeters per year, which essentially is as fast as your nail grows in 1 year. Now, on our human time scale, that is extremely slow. But if we are looking at the entire geologic history and our geologic timescale, which spans with the formation of the Earth about 4.56 billion years ago, that is extremely rapid geologically speaking. Now, the theory of plate tectonics, or in its basic sense, plate tectonics, states that the outer surface of the Earth is broken up into these coherent rock body slabs. Now, in its basic sense, these plates are not interacting intraplate, which means that these plates are not changing inside the plates themselves. They're changing and they're moving with respect to the boundaries of these plates, the edges of their plates. Now, we're going to talk about 3 main plate tectonic boundaries in the next couple slides here. We have 3 main types of plate boundaries, and those are divergent boundaries, convergent boundaries, and transform boundaries. Divergent boundaries literally means diverging, so the plates are moving apart. Converging boundaries are when the plates are being pushed together, so they're moving towards one another. And then you have transform boundaries, where the plates are sliding past one another. Now, if you notice on the screen that I also put hotspots. Now, hotspots are not a type of plate boundary, but they are really important when we get later on into Geology 100 lecture, especially when we start talking about earthquakes and volcanoes. Here's another look at plate boundaries. So throughout this PowerPoint, I have given several plate boundary animations that I highly suggest you all click through and take a look at. We have different types of divergent and convergent and transform boundaries. Remember, we talked about plate tectonics being the lithosphere that's broken up and fragmented into these coherent rock body slabs. And we know that Earth's lithosphere is broken up into 2 main types, which is oceanic or continental crust. With divergent boundaries, we have 2 main types of divergent boundaries. The first one, which I talked about a little bit earlier, which is Midoceanic ridges. Now, with mid-oceanic ridges and divergent boundaries, that is when 2 oceanic plates are being pulled apart. We also have continental rifting, which is also a type of divergence, and that is when 2 continental plates are being ripped apart. Then we also have convergence, and we have several different types of convergence. We have continental convergence, where you have 2 continental plates that are being pushed towards one another. We have continental oceanic convergence, when a continental and an oceanic plate are being pushed towards one another. And then you have oceanic convergence, when you have 2 oceanic plates that are being pushed towards one another. And then we have transform boundaries, which you can have oceanic transform, you can have oceanic continental transform, and you can have continental and continental transform, which just means that those different types of plates are sliding past one another. With Midoceanic Ridge, which is a form of divergence, you have two oceanic plates that are pulling apart. So this is just like the seafloor spreading that I talked about with Harry Hetz and Robert Dietz. A good example of a mid-oceanic ridge would be the Mid-Atlantic Oceanic Ridge, which literally extends all the way down to the reaches of the Atlantic Ocean. Here's a typical diagram of a mid-oceanic ridge, where on either side of this block diagram here, you can see oceanic crust, with the center, this being the mid-oceanic ridge axis, where you actually see the separation of these two oceanic plates. Now, I've talked about seafloor spreading, with thus being this hot mantle, this magma, is being pushed towards this mid-oceanic ridge axis and will thus cool in the form of lava and thus create very much new oceanic crust. The next type of divergence that we have is continental rifting, and that is when you pull two continents apart. So as you're pulling the two continents apart, the continents undergo extension, which means that they're just extending away from one another. Where that continent is extending, and thus you have this rifting, this area of this breaking, that crust is slowly thinning through time, and you get a rift valley that forms. Now, within this rift valley, because you have the thinning of this continental crust, you have this hot mantle, this hot asthenosphere underneath that wants to creep its way through because you are lowering the pressure. As you continue to tear these continents in two, you are simultaneously creating new crust, but you're also thinning it. And through time, that continental rift, that rift zone, that rift valley can slowly fill in and thus births a new ocean. But it starts off of a narrow sea, and as you continue rifting, thus extension of this crust, you will then form a new ocean, which is what we have seen through time. The next type of plate tectonic boundary that I would like to talk about is convergence. Now, we talked about three main types of convergence: continent-continent, continental oceanic, and oceanic-oceanic. The first one we have on here is Continental Collision. That was a really great animation and narrated figure video by Stephen Marshak, which is from the textbook in this course. Now, Continental Collision is essentially when you have two continental plates that get pushed towards one another. But because both continental plates, in its basic sense, they are very much thick. Remember, we talked about continental lithosphere can be anywhere from ranging from 30 to about 100 kilometers. Because they are both thick and they hit one another, neither one wants to be subducted underneath the other. So this is essentially how you create mountain ranges, where if they get pushed together and they don't want to go down, they're going to get pushed up. The next type of convergence that we have is continent versus oceanic. In continental and oceanic collision, the oceanic crust, because it is much thinner and denser material, because it is mostly comprised of basalt, will subduct underneath the continental crust. Now, essentially what this means is that this thin and really dense oceanic crust just gets swallowed underneath the continental crust. Now, in doing so, you can create these volcanic arcs, and that occurs due to partial melting because you have this oceanic crust that is now very thin and dense and saturated with oceanic water, so it is very much cold, will now be placed right next to this hot asthenosphere. And so in doing so, you can create some volcanic arcs. Now, we'll talk more about partial melting when we get into volcanoes and igneous rocks. The last type of convergence that we have is oceanic and oceanic convergence. Now, we've talked about our very much thickened continental crust, which is less dense than our very thin but dense oceanic crust. So what happens when you have oceanic and oceanic crust collide with one another? We know that subduction will occur because they are very much dense and they are thin. So with oceanic collision, the older plate will subduct because it is more dense than the younger plate. The last type of plate tectonic boundary we have are transform boundaries, and that is just when the lithosphere slides past one another. Now that brings us to the end of week 4's topic of the theory of continental drift and plate tectonics. Now the main things that I want you to get out from this week's topic is the change from the Alfred Wegener's theory of continental drift into the theory of plate tectonics. Now be very much familiar with Alfred Wegener's 5 main lines of observations. Be familiar with the mechanisms and the forces that had backed Alfred Wegener's beginning theory, which is seafloor spreading, the mechanisms behind seafloor spreading, and thus how plate tectonics interact with one another, which is along their boundaries. Having this basis knowledge of plate tectonics will help us later on in the course when we talk about earthquakes, when we talk about volcanoes, and even once we start getting into coastlines and glaciers.